Here, an online plug-and-play algorithm for regularized image reconstruction method is regularized image reconstruction plug-and-play prior regularization by denoising, iterative thresholding, alternative minimization, stochastic optimization, PNP SPGM. PNP SPGM is close to that of the batch algorithm with the final SNR for B equal to 10 and B equal to 30 being within 0.2 dB and 0.01 dB respectively from that of PNP APGM. Additionally, PNP SPGM achieves a significant speedup due to the reduction in per iteration complexity. Performance analysis of plug-and-play ADMM. A graphical signal processing perspective, high-trivia transaction, computational imaging. Plug-and-play ADMM concerns equilibrium. Image restoration, image denoising. A result is 32.97 dB obtained at eigenvalues of the inversion matrices defined in 54 and 55. We set rho equal to 0.005, mu naught equal to 1, mu I equal to 0.2 for I equal to 1 to 5. Optimization parameterized plug-and-play ADMM for iterative low-dose CT reconstruction. Low-dose CT parameterized plug-and-play ADMM deep learning parameterized plug-and-play alternating direction method of multipliers. 3PA ADMM LDCT image reconstruction. This method using the in 3P ADMM for those level of 20 milliamps, 12 milliamps and 4 milliamps obtained PSNR 39.2418, 37.9767 and 37.6605 dB respectively. MSV 0.0180, 0.0228, 0.0277 like this. NMSE for the BSNR value. For FSIM, BSNR value is 0.9477, 0.9477, 0.95252. Yeah, BSNR is this value. For NMSA, this value. For 20 amps, 12 amps, 4 amps. For 20 amps, 39.2418. For 12 amps, 37.9767. For 4 milliamps, 37.6605 dB. Like this, NMSC for 20 milliamps, 0.0180. For 12 milliamps, 0.0228. And for 4 milliamps, for 0.0277. FSIM for 20 milliamps 0.9477, for 12 milliamps 0.9477, for 4 milliamps 0.9252. Image restoration and reconstruction using target plug and play priors. Image restoration, image reconstruction, Gaussian mixers ADMM plug and play class adapted priors Gaussian mixer models. Gaussian mixer model, and then iterative shrinkage thresholding algorithm. Results corroborate the hypothesis that targeted periods lead to better performance not only in denoising but in other inverse imaging problems as well. Image restoration by iterative denoising and backward projections. Plug and play inverse problems, image restoration, image denoising, image deblurring, image impeding, denoising, neural network. IDBP, PM3D, recovery, BSNR versus iteration of house test image with 80% missing pixels and no noise, recovery of house image with 80% missing pixels and mu e, sigma e equal to 10. Denoising period driven deep neural network for image restoration. Deep neural network DNN, denoising based image restoration. Deep neural network denoising period images restoration. Convolutional neural network CNN, original images deployed by BEPLL 31.37 dB. C DDCNN 3354 dB for MEMNET 334.40 dB and D hours 33.80 dB. Results for 6th image of H14 for 5 cubic downsampling and scaling factor 4. The BSNR result DNRD 32.51 dB, VDSR 32.70 dB, DNN CNN 32.36 dB, MEMNET 32.79 dB, and for hours 32.88 dB. SR results for 7th image of set 5 for Gaussian downsampling with scaling factor 3. The BSNR results NCSR 35.74 dB, DDCNN 35.93 dB, MEMNET 36.92 dB, hours 37.75 dB. Plug and play ADMM for image restoration, fixed point convergence and applications. PM3D plug and play ADMM has a probe fixed point convergence. The low resolution input 5 cubic interpolation DCNN 24.19 dB bottom from left to right, SPSR 22.44 dB, PSE 22.80 dB, GPR 20.81 dB, hours M 23.49 dB. Plug and play ADMM has performs better than several existing methods. Plug and play ADMM performs better than several existing methods. Performs better than several existing methods. Loss functions for image restoration with neural networks. Image restoration, neural networks, loss functions. Average value of different image quality metrics for the networks trained for denoising, demosaicing with alternating loss functions. Visual results of the network trained alternating loss functions in mostly flat regions. Larger values of sigma help reducing the virtually artifacts. From the literature survey, we analyzed the issues of results corporate the hypothesis that a targeted price lead to better performance not only in Results corroborate the hypothesis that targeted periods lead to better performance not only in denoising but in other inverse imaging problems as well. The convergence behavior of PNP star in terms of SNR dB for identical experimental setting by additionally including the SNR performance of LESO. Theoretical convergence has practical importance. It provides a mathematical justification to terminate the algorithm after sufficiently many iterations. Then in the pre-processing stage, denoising and normalization operations are employed in order to prepare the input images for the next stage. Okay. Then restored images obtained using scaled PNP ADMM, PNP ADMM and standard PNP ADMM respectively. The modified PNP algorithms are shown to produce good restorations in the classification stage. The CNN is used. PNP star converges for a class of linear problems using kernel denoisers. The problem of convergence can be reduced to that of the stability of a dynamical system in plug-and-play realizations. The knowledge of the forward model is combined with powerful denoiser to obtain state-of-the-art image reconstructions. Related experiments are also present in empirically confirm the proposed propositions and elucidate the higher efficiency of PNP FPGA in different representative situations. In the flexible PNP framework to tackle a variety of inverse imaging problems under a GMM patch-based image creator. Inverse problems appear in many applications such as image deep learning and in painting. The task was formulated as a regularized inverse problem that was subsequently transformed into an iterative form by relying on the ADMM and plug-and-play frameworks. Connection between scaled proximal maps and the PNP realization is novel, reduces computation complexity and limiting the amount of computer memory. Additional provides less loss. Field algorithms achieve state-of-the-art performance in a range of imaging applications. PNP and neural networks provide a means of optimizing initial data input via weighting certain aspects of the input to produce an optimal result. Map denoiser DAER. Figure 1. Our end-to-end training of MAP denoisers using trained DAES. The DAER is used to enforce the regularization term for optimizing D. At the same time, the output of the network D is kept close to its input using data loss. Map denoiser, data loss, data loss, DRV, then input given to DAER, register loss, R dash of D of V. Here, the iterative result is, this iterative result of our MAP denoiser network, top row and the residual with respect to input images, bottom row, original, iteration 4, iteration 8, iteration 16 corresponding. Okay. Convergence speed comparison of an image from BSDS 300. Note that the DMSP and the proposed method try to optimize the same object. Using the ADMM approaches, we can speed up the optimization up to 70x cluster. Here, iteration 0 to 300. Here, BSNR 20, 22, 24, 26. We are also 0, 50, 100, 150, 200, 250.